This problem is like our example from the inclined plane demo video. And like all other problems that happen on planet Earth, there is gravity to contend with. And that's really why these blocks are moving in the first place. Gravity is always pulling objects towards the Earth at an acceleration of 9.8 meters per second squared. I'll read the question. A block starting from rest and a height of 10 meters slides down a plane inclined at 45 degrees to the horizontal, or to the ground. What is A, the magnitude, and B, the direction of the final velocity of the block? Given that we are working with initial height and initial velocity, energy conservation is the most straightforward way to solve for the magnitude of the final velocity. Like we did in the freefall problem, we'll start by writing down the equation for energy conservation. You could pause right here and see if you know how to write it in terms of kinetic and gravitational potential energy. Then check back to see how we match. If you've given it a try, here's what I wrote down. The initial kinetic energy plus the initial gravitational potential energy equal the final kinetic energy plus the final gravitational potential energy. We can rewrite this as 1/2 times the mass of the falling object or moving object times the initial velocity squared plus the mass times gravity times the initial height. Those two terms are the initial energies. And those equal 1/2 times the mass times the final velocity squared plus the mass times gravity times the final height. As you can see, there's a mass term in every one of these individual terms of energies. What we can do in that case is we can cancel the mass in the potential, in the kinetic, in the potential, and in the kinetic energy. This means that our problem, our solution, will be independent of mass. Okay, the next thing I'm going to do is I'm going to highlight the knowns in the text and in the figure that correspond to the variables in our problem. This is a good practice to incorporate in your own problem solving. You can pause here, see if you can find all of the variables, and then check back. I'm going to now highlight. The first variable that we have is the initial velocity that we see here. I've highlighted it in blue. V sub I. Well, the initial velocity we get from the text, and that says we're starting from rest. So that would be right up here at the top. They're not moving when they start. The next piece we need is the initial height, h sub I. And we can get that either from the diagram or from the text, which says that it's from a height of 10 meters. The next piece we need is we can look at the final velocity. That comes up next. But you'll notice that we are asked to find the final velocity. This is not a known from the text, but this is actually what we're going to be solving for. So we would call this the unknown. And the last piece that we have is h sub f, which is our final height. And our final height is down here at the grass, where it's reached the ground. We can make a list of these, and our known and unknown values. And what you see is we know that V sub I equals 0 meters per second. That's from rest. H sub I equals 10 meters. And H sub F equals 0 meters. Our unknown is V sub F. That's what we're being asked to solve for. Next, I'm going to substitute our knowns into the energy conservation equation. The knowns that I'm going to substitute in first are V sub I and H sub F. And I'm going to do that because those are both 0. When I do that, this term becomes 0. That's the final potential energy term. And the initial kinetic energy term is also 0. That leaves us with just the initial potential energy term and the final kinetic energy term. I'm going to switch the order so that the V sub F term is on the left. So that's 1/2 V sub F squared equals G times H sub I. Solving this for V sub F is done in detail in the energy conservation solution for free fall. I'm just going to write this down. We multiply the 2 onto the other side and take the square root. V sub F equals the square root of G times H sub I times 2. I'm going to start a new page, and I'm going to rewrite our equation at the top of the page. So we have V sub F equals the square root, and I'll put the 2 on this side, 2 times G times H sub I. Now, because we didn't substitute in a number for H sub I, we can see the relationship between the final velocity and the initial height. And what we can see is that the final velocity depends only on the initial height. And is a square root relationship. From our list of knowns, we can substitute H sub I and G into our equation. Remember that we have to do units as well. So V sub F equals the square root of 2 times 9.8 times 10. And the units, 2 has no units, but gravity has units of meters per second squared. The height has just units of meters. Multiplying this through, we have the square root of 196 and the square root of meters squared per second squared, which equals 14 meters per second. That's great. Again, these are the correct units for velocity, and we have a magnitude. So we've answered part A of the problem. Note that 14 meters per second was also the magnitude of the velocity for a ball that was falling free fall 10 meters from the ground. This is essentially a very important piece of the energy conservation concept, and that's that the energy as it changes from potential to kinetic is independent of path. So whether you're in free fall, whether you're on an inclined plane or on a half pipe, once you've undergone a height change of 10 meters, your speed in magnitude is going to be 14 meters per second. The direction of our final velocity is found using the geometry. I'm going to re-sketch so that I can draw on it a little bit of the plane here. So let's say we have a plane going down this way. Here's our block going down the plane, and we have our final velocity. I'll put that in red down here. Well, this is really a right triangle, and this is some angle. We could answer this for a 45-degree angle or a 23-degree angle. So the final velocity is going down this hill in line with the inclined plane. And now let's actually put this inclined plane even longer. And we're going to transpose on top of it a axis. So here's the y-axis and here's the x-axis. And our velocity, well, the secret is going to be out very soon. The velocity is actually a vector. It has a magnitude and it has direction. And this is a good point to learn to deal with vectors. When we ask for the direction of something, we mean if it started at the origin, which way would it be pointing to? What's the angle associated with it? So we just replace this tail at the origin, and we see, that's not particularly accurate, what we see is that we're at negative 45 degrees below the x-axis, really. But some textbooks, sometimes the proper answer for a problem is a positive number for the angle, and so you need to be able to write this as a positive number too. And to do that, you actually start at the x-axis and go all the way around and come back to that same line that your vector is on. And this one would be 360 minus 45, which would be 315 degrees. That would be the positive number. If we were to do this for theta equals 23 degrees, so let me go back. So the answer to A was v sub f equals 14 meters per second. That's the magnitude. And the answer to B is 315 degrees for the 45 degree incline. And, well, we have to do 360 minus 23 for the other, or let's write this down, minus 23 degrees for the 23 degree answer. Most of the time, you could write them down either way. This is a more correct way to write that. Okay, the last part of the question was, how does the final velocity and the angle depend on the inclined plane? Well, the final velocity is independent. It doesn't depend on the angle. It doesn't depend on path at all. So this is path independent.